Okay, I've had some requests for more practice problems, so here we go. Thermodynamics problems. So I'm going to start with how to determine the equilibrium constant from free energy. And I'm not going to do this with any sort of numbers, because it doesn't really matter. So we know that the given is R, the value for R is 8.314 joules per Kelvin mole. That's going to be given to you on the exam. Okay, so we have a bunch of equations for delta G. So delta G equals delta H plus T delta S. We're not given, none of these are the equilibrium constant, so this is not the correct formula to use here. We also know that delta G equals either delta G naught or delta G naught prime plus RT natural log of KEQ. Okay, so this right here, this is the equilibrium constant. Equilibrium constant. Okay, so if we're using the equilibrium constant, then we know, therefore, this is at equilibrium, and therefore delta G equals 0 at equilibrium. So if we're using the equilibrium constant, this equals 0. So 0 equals delta G naught or delta G naught prime plus RT natural log of KEQ. Then we can move this delta G over here, equals negative RT natural log of KEQ, and the goal here is to solve for the KEQ. So then we're going to divide both sides by RT, and we end up with the natural log of KEQ equals whatever value you got for delta G over RT, and this whole thing is negative. Okay. So R is a constant, temperature will be given to you. If it's not given to you, you can assume that it's 25 degrees Celsius because this is standard. And then to get rid of the natural log, all you have to do is take e to both of these sides. So e cancels out the natural log, so we get KEQ equals e to the negative delta G over RT. Delta G standard or biochemical standard. Both of those would work there. And then at this point in the problem, you would just plug in whatever value you have for here for this delta G, and that's how you solve for KEQ given a standard delta G and equilibrium. Okay, so next up, what happens if it's not at equilibrium? Okay, so we start with the same formula, right? So it's not going to be delta G equals delta H minus T delta S. So non-equilibrium Q, find Q. Okay? So it's not going to be this equation because this isn't going to give us Q. So remember, Q is the mass action ratio. It means the same thing as the KEQ, except this is not at equilibrium. This is at any other point in time, non-equilibrium. So because this is not at equilibrium, therefore delta G does not equal 0. Okay? And therefore we can't use KEQ, but really the only difference is those two things. We can use the same equation. So delta G equals standard delta G or biochemical standard delta G plus RT natural log, and instead of KEQ here, it's just Q. And you would solve this the same way. Okay, but because delta G is no longer 0, because this is not at equilibrium, you're going to have a value for delta G. So delta G minus the standard delta G, which is a physical number that you will either find or be given, is going to equal RT natural log of Q. Okay, so then we have to take this whole value and divide it by RT. So we get the natural log of Q equals this whole thing, delta G minus delta G naught prime, divided by RT. And again, we need to get rid of this natural log, so we're going to raise this entire expression, both sides, to the E. Okay, so this cancels out, and we end up with Q, the mass action, is going to be E to this power, whatever what ends up being these values, divided by RT. Remember that this has to occur at one specific point. So R is going to be constant, temperature is going to be constant, because we've got this value right here. This requires one single temperature. And the delta G is going to vary based on the temperature and all these other conditions. So you'd be given delta G naught prime, and maybe the temperature. And then you can solve for Q. Okay, so if you needed to solve for a specific ratio of product, right, so this is going to equal some number, right? So, and this is A plus B. This Q can represent this reaction, C plus D. This is the reaction from the book. I love this reaction, right? It's wonderful. It's so simple. So Q here would equal the concentrations of the products raised to the moles of the products, if that's a thing, concentration of big D to the little d, over concentration of A to the little a, concentration of B to the little b. Okay, and if you're given 3 out of these 4, then you can actually solve for the other one. Like, say we're not given C, so what's the moles of C? So we have this number from up here. We can calculate this based if we're given delta G naught prime, and if there's a specific temperature. We can figure out Q. Then we can plug in that number here, and if we're given all the other numbers except for C, concentration of C, and we're given a number here, and a number here, and a number here, we can solve for C just by multiplying by these bottom numbers and dividing by the top number. So C, the concentration of C, is given that way. So this is all just sort of common algebra type problems. So you need to stop thinking about this as thermodynamics and start thinking of it as, what are my givens, what formula do I use, how do I solve for X? That's the trick to the thermodynamic reactions and equations. How do you solve for what you need, and what equation do you use? Okay, the next thing we're going to talk about is that free energy and also some other values. Delta H is a state function, free energy, which means delta G. And so what this means is that it doesn't matter how you get to the end. All that matters is the initial state and the final state. Okay, so that's all that matters. So if, for example, we are trying to make some product. A plus B makes C, and then C makes D, right? There's a delta G for this reaction, a standard delta G, probably biochemical standard delta G. We'll say that this is positive 10, and it can be given to you in kilojoules per mole or in joules per mole. And let's say that this is negative 20 kilojoules per mole. So in order to find the delta G naught prime of AB going to D, all we have to do is add these up. Okay, so C's on both sides are going to cancel out, and this will give us A plus B going to D. This is what we want. And then we just add. So this is negative 10 kilojoules per mole. Okay, so this would be favored, and the products are favored also, right? So this is pretty favorable reaction. So we see a lot of this in biochemistry is we can take an unfavorable reaction like this first one and then couple it to a favored reaction, and we end up with an overall favored reaction. Okay, so what happens if, in the same example, we have A plus B going to C, but then we only have information for D going to C. So the delta G naught prime maybe is, we'll keep it the same, 10 kilojoules per mole, and the delta G naught prime here is 20 kilojoules per mole. Okay. So in order to solve this problem, first we'd have to flip the bottom. Because C's don't cancel, they're both on the same. So if we added it up right now, we'd get A plus B plus D makes 2C. And that's not what we want. We want A plus B going to D. Okay? These two are not the same. So in order to do this, we must flip the bottom reaction. And when you do that, the delta G becomes negative. So A plus B goes to C. When we flip this, C then goes to D. Suddenly this is a product, this is a substrate, this is a product, and then we're going to get the reaction we want. A plus B goes to D. So what we do over here is you simply flip the sign. So we have 10 kilojoules per mole, and here it used to be positive, so now this is negative 20 kilojoules per mole. And you can do this for any state function, not just delta G's. Okay, and we end up with negative 10 kilojoules per mole, exactly what we solved for above. So you just flip the sign. Okay, so now we're going to talk about reduction potentials, which is the last part of this chapter. So the equation we have for reduction potentials, remember this is going to involve an oxidant and a reductant. And the way you can figure out oxidation and reduction, I'm just going to use my favorite example, C6H12O6 plus 6O2 makes 6CO2 plus 6H2O. This is the overall equation for glycolysis. This is a redox reaction. So if you look at this glucose, gosh, that took me a minute. If you look at glucose, you notice that there's equal numbers of carbons and oxygens, and there's a lot of hydrogens here. So because there's twice as many hydrogens as anything else, it's very likely that this is reduced, right? And that is what's true. So this is the reduced form. Now if we look at oxygen, this has no H's on it, so this is oxidized. This is the oxidized form. If we look over here, this has no H's on it. This is the oxidized form. And here we see H's. This is reduced. Right? This is a very clear-cut example. You can also think about reduction and oxidation in terms of Leo the lion says grr. Right? So losing electrons is oxidation, gaining electrons is reduction. Okay, so if it starts out reduced, it has lots of H's on it. These H's also carry electrons. These protons carry electrons, right? That's what hydrogen does. So this is in the reduced state. This becomes oxidized. This is in the oxidized state. This becomes reduced. Okay, so what starts off as reduced is called the reductant. And it becomes oxidized. What's oxidized becomes reduced. This is called the oxidant. This causes oxidation of that. So these two things are combining. This is the reductant, this is the oxidant. It's very, very difficult, so when you get these questions on an exam, you need to stop and think. Where are the electrons? Where are the protons? What's being reduced? What's being oxidized? So another way to write this is oxidant is going to gain electrons, so it has n number of electrons, and become a reductant, which is then reduced. So the equations that we can use to answer questions involving redox, which is very, very important in biochemistry. Delta G naught prime, the standard biochemical free energy, equals negative N Faraday's constant change in electron potential. I'm sorry, reduction potential. Okay, so if this is a really big number, then that means that the pair is more likely to participate in redox. Okay, so we can figure out delta E naught prime, that's equal to delta E naught prime of the electron acceptor, so that would be the oxidant, minus the electron donor, the reductant. Okay, so oxidant minus reductant. Okay, and in this type of situation, you'll be given a table with these values, and you simply just plug and chug. F would be Faraday's constant, that would have to be given to you. And N, this is the number of electrons in the balanced half reactions. Balanced half reactions. Okay, so remember that as you're writing the half reactions, the values of delta E naught prime don't change. Okay, so one example of this is if we take ethanol plus NAD plus to make acetaldehyde, plus NADH plus H plus, right? Okay. So we can write this in terms of two half reactions. This is the overall equation. We're trying to figure out the free energy of this. So we've got, we've got NAD plus becoming NADH plus H plus. Oops, wrote that wrong. We've got, I wrote down the wrong half reaction, sorry. NAD plus H plus, there we go, plus 2 electrons makes NADH. Okay, so this makes sense because this is oxidized and this is reduced, so we have to gain electrons on this side. Okay, then we've got acetaldehyde, and I'm just copying these down from a table in the book, plus 2H plus 2 electrons, and that's going to make ethanol. Okay, so in order to solve this, we need to flip the bottom one. And here we've got some standard reduction potential, negative 0.315. This is in volts. And the standard reduction potential here is negative 197. Whew, I'm bad at copying today. Forgive me. Okay. And we need to flip the bottom. So, I'm just going to put it in brackets and flip it right here. So we end up with ETOH, because we want that on this side, the left side of the equation, is going to make acetaldehyde plus 2H plus 2 electrons, and we do nothing to the standard electron potential. So those electrons are going to move no matter what. And that's, of course, in volts. Okay, so to figure out the delta E naught prime is the first step, and so that's delta, no deltas yet, so that's the standard electron potential of the oxidant, the electron acceptor, minus that of the electron donor. And so this is a pretty easy example because when we flip it this way, these cancel, the electrons cancel. We don't have to worry about anything. Everything's already, we don't have to multiply by anything. This is a very easy example, right? So we just have to figure out what's the acceptor and what's the donor. So looking at the overall equation, we know that NAD starts off as the oxidant. So this is going to accept the electrons. So we need the NAD plus half reaction number right here. Okay, so that's negative 3.15, 0.315 volts. And then the electron donor would be the ethanol. And that makes sense because it's got an H, this one doesn't, minus negative 0.197 volts. Okay, so this ends up adding, and you end up with a value of negative 0.118 volts. You then take this standard reduction potential, plug it in here. This is given to you. This is 1. We get delta G naught prime. Oh wait, I'm sorry. Because there was 2 electrons here, it's 2. Right? So, negative 2 electrons were involved in this. This is Faraday's constant. It will be given to you. And we just solved for delta E naught prime. And that's how you can solve for the standard free energy based on the standard reduction potential.